Hey guys, today we're going to be looking at combination sum. This is part of the grind 75 problems that we've been working through. And it is one of the harder ones that we've done up to this point. And so let's just read the description. Given an array of distinct integers called candidates and a target integer called target, return a list of all unique combinations of candidates where the chosen number sum to targets. You may return them in any order. The same number may be chosen from candidates an unlimited number of times. So two combinations are unique if the frequency of at least one of the chosen numbers is different. It is guaranteed that the number of unique combinations that sum up to the target is less than 150. Okay. And so here we have candidates. So let's go ahead and do like a simpler example. And so we'll do 2, 3, 5. So example 2, but we're going to say the target is going to be 6. Okay. So let's go ahead and look at that. Okay, so here we have 2, 3, and 5 with the target being 6. Now, our first intuition is that this could be a tree kind of structure. And so what we want to do is, in creating this tree, what we want to do is, so we start off with this empty array, and then over here, we're going to pass in this value, okay? And so, so we have a 2, and what we can do here, and over here, we're going to say we don't want any 2s, okay? And so it's going to be a blank list of some sort. And so over here, what we want is we're going to say, well, we have 2s, and I want another 2 added onto this. And so here we'll say 2, 2. And then over here, we're going to say, I'm not going to add any more 2s to this list. And then over here, we're going to say, well, maybe I'll add another 2 to the list. Okay, 2, 2, 2. And over here, we're going to add no more 2s to the list. But over here, we have identified a target. Okay, and so this gets added to our return list. And over here, we said we're not going to add any more 2s, but let's go ahead and start adding some 3s. Okay, so we have 2, 2, 3. And we see 2, 2, and 3 add up to 7. That's no good. And then over here, just to save a little space, we're going to say 2, 2, 5. And we know that that's going to be too big. All right. And so over here, we have our single 2, but we said that we're going to add no more 2s on this side. And so what we're going to do is we're going to say, well, what about a 3? So we have 2, 3, and this is 5. Over here, we're not going to add any 3s, and this is just going to be a 2. And then over here, we're going to say, well, what about a 2, 3, 3? Nope, too big. And then over here, just to save some space, we're just going to say 2, 3, 5. Okay, so that's no good. And then over here, we can't add any more 2s or 3s. We're only adding 5s, and we get down to a 2 and a 5, and that's too big. Okay, and so here we said we're not going to add any more 2s to this side. And so we can add a 3, and I'm just going to bring it over here. And so here we can add a 3. Or no more 3s. Okay, so a blank array. And then over here, we can add another 3. And we have identified a target. And then over here, we can add no more 3s to this side. And then over here, we can add a 5. And too much. And we're not going to continue because over here we're not going to add any 5s, and so this would be our index going above the length of this, or equal to the length of our candidates. Okay, and so over here we said we're not going to add any more 3s over here, but we can add a 5. So we have this 1 5 that we can add. And, there's not much you can do here. We can add another 5 to see if we can hit the target. And we have gone over. Okay, so inside this example, we have identified two values, two sets of values that would equal to our target. And so you get the general idea of backtracking in this tree and getting these two targets, and that's exactly what our algorithm is going to do. Okay, so let's go ahead and code up this and see what that looks like in code. Okay, so this is going to be recursive, and so we're going to have to define a recursive method as well. But our main method, we're just going to create our return list. Okay, and so that's going to be this is saying that this is our return type. So we're going to create that list, and we're going to say list, and it's going to be a list of integers. We'll call this return list. All right, cool. And here we're going to call our recursive function. Now we haven't defined this yet, but so maybe we should probably do that now. Okay, and so here we're just going to take in all those variables that we need for this to be successful. So public list of list integer. Okay, and we'll just call this DFS, depth first search. And so what we want to do here is we have int I list, and this is going to be our current list. We'll call it current. So here, let's see if I can get rid of that. Okay. So here we're going to have int total. That's going to be our target value. No, that's going to be our current total. And here we're going to have int target. And then our return list, we're passing that in. And so I'm just going to copy this. And then our candidates. Okay. So here what we have, basically we have our base condition that says if total is equal to target, we're gonna add that to our return list. So we're gonna say return list dot add, and it's going to add in the current list that we're building up. Okay, array list. Wait, a new array. Oops, array list, and we're going to add that in. Okay, and so here what we want to do is we also have another condition that says if I is greater than or equal to candidates.length, or total is greater than target. So if this is true, we're just going to say return null. Okay, and then here we could actually return null as well. All right, and so now what we want to do is, these are basically our return value. Like, they're going to get us back up the recursive call. Now, what we want to do is go down the recursive call. So we're just going to say current.add, and we're going to add in the candidates to our current list at our current index. Okay, so candidates at I is going to get added. So if we're just starting out, this is going to add that 2, that initial 2. All right. And then we're going to call this function again. So we're going to say DFS. We're going to pass in our current I, our current array, our array list in this case. So we're going to say total plus candidates at I. Then we're going to pass in our target, return list, and candidates. Okay, and then we want to say, well, I don't want the next call to include any 2s. Remember, one side of the tree is going to include 2s, and then the other side is we don't want any more 2s. And so what we're going to do is we're going to say current dot remove, and then this is current dot size -1. Okay, so that's going to remove that element from our current list, and then we're going to make this call again, except we're going to say, well, our index is now 1 past what it was, and so this was giving us values of, if this were starting this process, this was giving us values of the 2. Now we want to see values of 3 and so on. Okay, and so once these return up, then we can say, once they find their answers and they have fully returned, we can return the return list right here. Now this return list is basically this inner array that's being passed in as a parameter. And so this is going to be then passed out when we make the call up here. And so we can just say return list is equal to, and then this is going to be our initial DFS call, 0 array list, 0 target return list candidates. Okay, and then we're going to return our return list, and I guess what we could just do is say return this. Okay, we don't have to return our return list, we're setting it and then returning it. We can just return it right here. So we'll go and run that. Let's see here. Oh, typo, no big deal. Candidates. All right, we got it. Okay, it's saying wrong answer. So what are we doing wrong? It has to be down here. So if total is equal to target, return list. Oh, so down here, we don't want candidates at I. Okay, So this total is just going to be the current running total. It's not going to include candidates at I. Okay. Okay, let me go ahead and pop this over. So, you know, we have good run time, time complexity. So let's talk about time complexity. So time complexity of most backtracking algorithms, well, it depends on how many recursive calls. But basically, we care about how like the height of the tree, okay? And so that all depends on our target. So if our target is 7, so for instance right here, our target is 7, we could potentially have a value of 1 here. And so we would have 7 levels to our tree, okay? And so what this is going to be is 2 to the power of our target. All right. Now imagine this were some huge number. Okay. Let's not say 7. Imagine this were, let's say 200. Now this is going to get real crazy pretty fast. Okay. So these numbers are probably going to stay fairly small because 2 to the power of n gets big really, really fast. So that's the time complexity, and then it's just O of n for the complexity for space complexity here. So yeah, that's it. And so if the explanation and the code is something that you found useful, please like and subscribe. If there's anything that you had questions on, go ahead and ask in the comments. If there's anything that you saw that I did wrong, go ahead and put those in the comments as well, because you know I love to learn just as much as the next guy. So even though I'm putting this out there as something for other people, you know, I'm trying to better myself in the process as well. So like and subscribe, and I will see you in the next one.